Chapter 2 is called Quantum Mechanics, and quantum mechanics deals with subatomic particles. It's an advanced field of physics and chemistry, two complicated fields of science colliding, so to speak. Why should you have to learn about this in your first chemistry course? Already in the second chapter? Alright, well, don't be scared. Okay, we're going to focus on a very narrow aspect, the electron of the atom, which is a subatomic particle. And if we understand the electrons better and how they behave, we can learn more, understand bonding, reactivity, and the periodic table. So we're going to focus on it, and it's actually not that complicated, so don't worry. Alright, so we're going to look at electromagnetic radiation. You've used a microwave, you've been exposed to electromagnetic radiation. You have a cell phone, same thing. Listen to the radio, we make use of the electromagnetic spectrum or the radiation. And then, so it's about light particles or the speed of light. And so just bear with me and it'll all come together at some point. So light particles, subatomic particles, don't behave like larger bodies of mass like baseballs, soccer balls, or bullets, right? They follow the laws of classical physics. So if I throw a ball and I can measure its momentum and its direction and take the gravitation into consideration, I can predict where that ball is going to fall and how it behaves every single time. Now, subatomic particles don't follow the laws of classical physics. Okay, so this radiation travels in waves, right? And so you have this wave, an electromagnetic wave, and that wave has two components, right? It has a wavelength here, lambda, and it has a frequency, how many times per second it goes up and down, okay? And that's mu. And the product of those two, lambda times mu, is always equal to the speed of light. So that's a constant here. So obviously they're light particles. The sunlight are photons or light particles. They travel at the speed of light. But they still have two components. They can have different kinds of energy depending on their ratio of wavelength to frequency. All right. Okay, so this is just a summary of and so this wavelength is usually measured in meters. And here's the formula. C is the speed of light here. 3.0 times 10 to the 8 meters per second. Alright, is equal to the frequency, which is measured in per seconds, or sometimes we just change that to hertz. Those are interchangeable. And meters. Okay, wavelength. Oh, Endergy. Alright, that's just great. Alright, so typo there. Sorry about that. Waves and energy. Alright, so you can actually relate the energy of a light particle according to its frequency, which is shown above here, right? So if you have you have two different waves here. One has high energy. That's this one here with 8 hertz. It goes up and down 8 times per second, right? If you count this here, 1, 2, 3, 4, 5, 6, 7, 8. Right, it goes up and down 8 times per second. So it has a higher frequency than the wave above. It only goes up 4 times per second. So 4 hertz is the same thing as, or hertz is the same thing as per second, second to the -1, right? This is just a measurement, but the units, so those are interchangeable. And so something that goes up and down faster per second has higher energy. So the shorter, these are inversely proportional wavelength and frequency, right? So the shorter the wavelength, the higher the frequency, the higher the energy. The longer the wavelength, the smaller the frequency and the lower the energy. So those two are related. And so this is the entire electromagnetic spectrum, all the way from high energy to, or from low energy here, right? From long wavelength or low frequency, like those radio waves here, and then all the way to gamma rays and X-rays. So gamma rays are very high energy light particles that are very damaging to your skin or to cells in particular, right? And so we can actually see some of that electromagnetic spectrum, and that's in a very narrow range between 750 nanometers, between four. I should go from low to high, from 400 nanometers to 750 nanometers here. Now, take note that except for that visible range, which we convert to nanometers, the light spectrum is usually measured in meters, or it needs to be. If you're going to use the speed of light equals mu times lambda, you will have to use meters. And so if I give you nanometers, you're going to have to convert that to meters, right? And so if you remember, 1 nanometer equals 1 times 10 to the minus 9 meters, then we can, for example, convert 650, this is just a review, 650 nanometers times 10 to the minus 9 meters for every 1 nanometer, right? So that's supposed to be a nano, not a millimeter, it's a nanometer, an N. And so that goes to 6.50 times 10 to the minus 7 meters. So that's just a quick review here. All right, so we have these two formulas here. We have energy equals H, which is Planck's constant, and obviously that will be provided to you down here in joules times seconds. Units are always important. And then the other formula here, C equals mu times lambda, the speed of light, and so those two you'll have to know. And we are going to work a few problems with that, right? So for example, what is the wavelength of light that has a frequency of 7.5 times 10 to the 14 per second, right? Okay, that's easy. So we just use C equals nu times lambda. And so I solve for, I want to know wavelength, so I need to know lambda equals C over nu, right? So C was 3.000 if you wish. It's a constant, so we don't worry about significant figures. We only worry about the two that are provided here in our measurement, times 10 to the 8 meters per second, divided by 7.5 times 10 to the 14 per seconds. Per seconds cancels, and the answer is in meters. And so that turns out to be 0.4 times 10 to the negative 6 meters. And if you were to, I'm not asking that to convert that to nanometers, but if you wanted to know if that's in the visible range, you would have to convert that. So 0.4, if I ask you what color it is, for example, times 10 to the minus 6 meters times 1 nanometer for every 10 to the minus 9 meters equals 0.4 times 10 to the 3, which is 400 nanometers. But if I don't specify, if I just say wavelength, if I don't ask you what unit, you can stop here, and you might want to do this. You might want to move this over so that we have the right number of significant figures. So it's going to be 4.0 times 10 to the minus 7 meters. All right. Another one here. What is the frequency of light that has a wavelength of 450 nanometers? So here you now need to convert nanometers to meters because the constant, the speed of light, is in meters per second. So, but we can put this all together in one formula. So you can have nu equals C over lambda. C is 3.0 times 10 to the 8 meters per second. and then I have 4.50 times 10 to the 2 nanometers. I just put it into something where I can just deal with the exponents here, times 10 to the minus 9 meters divided by a nanometer here, right? So my H's look like N's, so just have to also listen to what I'm saying. So nanometers cancels, and then this turns out to be 6.6 times 10 to the 14 hertz, or per seconds, or hertz, interchangeable, right? Okay. What is the energy then of 450 nanometer light? We can use the frequency that we calculated earlier. Energy is going to be equal to H, which is Planck's constant, times mu. So we get energy equals 6.63 times 10 to the negative 34 joules times seconds, and times the frequency from the previous problem, which is 6.6 times 10 to the 14 per second. So seconds divided by seconds goes away, equals 4.4 times 10 to the minus 19 joules. That's the energy of a photon or a light particle that travels at this wavelength, 450 nanometers. All right, let's dig deeper. Why do we care about these light waves, and care to study this? Okay, Planck's constant, right? What he did, they were studying solids. So he took a piece of iron and he heated it up, right? And so if you take a piece of iron and you plot temperature versus energy, and I'm talking about thermal energy, right? What happens, obviously, as you heat up this item, it's going to pick up thermal energy, and you'll see a linear increase in energy. But if you do this for the energy of the electromagnetic spectrum that's given off, that's not what you see. All right, what you will see is you don't see this red glow, and so this shows the red and the white glow here. It's kind of looks like there's a red to yellow to white, so it's not a great picture. But let me back up a little bit here. So okay, so if you heat this up, you're going to see the same light spectrum given off. It's going to be silver. You go all the way to 300 degrees and it's just going to have that silver shine to it, right? So at 300 degrees Celsius, it will then all of a sudden start glowing red. Poof, right? So that means the energy of the light that you see that's given off by the piece of iron just went up in energy, all right? And then as you heat that up, it's going to stay red until you hit about 1200 degrees. At 1200 degrees, it's going to glow white, which is what we see here. So poof, the energy goes up again, right? So what that told Planck is that the energy of the electromagnetic spectrum has to be quantized, right? It either has energy 1 or energy 2 or energy 3. So we have these quantum levels, and so and then the energies of the electron, the magnetic spectrum that we see from the solid, right? And see, so the piece of iron here has 26 electrons, okay? And so what we see is the energy transitions of these electrons. As we heat it, the electrons are promoted to higher levels, and when they come back down, we see energy. And so there's a ton of different possibilities here, all right? So, and the reason we see red to white and yellow here, this funky transition, is because you probably have a temperature. The temperature is in between uh, it's right on the border of the 1200 here, right? So you have, but it for as far as electrons is concerned, they either are one way or another, right? So this is what's shown here, right? We have these quantized energy levels, right? If you have an electron in iron, it's either going to be here or here or here. It's not going to be in between, okay? So there's no such thing. It will jump up, right? It will either jump up or down. And so if you put shine energy on it, if you shine light on a piece of iron, it's going to bounce back, and you see the silver color of this metallic shine of piece of iron, right? And then that's what you see, because when the energy of the electron is released, when the electron comes back down, right? So what goes up comes back down, right? Okay. And another person that was involved, we have Niels Bohr, who comes up in a minute. You've got Erwin Schrödinger, which I kind of totally glanced over in the beginning, and you also have Albert Einstein, who worked, of course, with quantum mechanics. And so he found that what happens is a photon or a light particle is ejected, right? When you energize any matter, the electrons go up, and then when the electrons come back down to a lower energy level, energy is of course released. So here is the relative level of the energy levels here, right? So we have several. We have quantum level n equal 1. That's the lowest energy level. So an element like hydrogen is going to have one electron, and that one electron is going to be on this low level here, right? And then if you go to helium, there are two electrons. There can be another electron down there. And then you've just filled up the quantum level, the capacity of the first level. Only two electrons can fit on this first level. And that explains why the first period only has two elements shown. It can, once you have a third electron, it goes to the second energy level. And the second energy level is quite a bit higher, right? Okay. And so the second quantum level can have 8 electrons, the third can have 18, and so the higher you go in quantum level, in energy level, quantum level, same thing, the more electrons you can put on a particular level, right? So it's the further away you are from the nucleus, the more electrons you can put around it. What is also interesting or noteworthy is that the difference in energy level from the first to the second is rather large. And as you go up higher, that energy level decreases. It's shown here, right? All right, so if you have something in the Bohr model, is all about hydrogen. And so there's just there's one electron here. That's it, right? So we've got one electron, and this tube here is filled with hydrogen gas. It's hooked up to two electrodes. It was evacuated, filled with hydrogen, sealed off, and there are two electrodes, and if you energize it, you see this white light. So that's a combination of all of the energy transitions that we can see. What you have is you put so much energy in it, you can have this single electron will go up to the second, the third, the fourth, the fifth, the sixth, and probably even the seventh. And then as energy is released, you can see you have all kinds of transitions here. You can have, let's say it goes up to the fifth, it can come down to the fourth, or it can go to the third, or it can come all the way back. And so what you see is only the combination of all of the energy transitions that fall into the visible range, and they all overlap, right? But you can actually split this through a spectrum, a prism, right? So if you take this blue light and you hold it to a prism, it's going to split into a so-called line spectrum, okay? So it's going to show you the exact energies, not just red light and yellow light. It's not going to split this into all these different colors. It's going to be specific to these energy transitions, okay? So let's just look at this first line here. So let me go back. So hydrogen, let's just look at this one here. We have in the visible range, right, there's 400 nanometers, 750. So going outside of that means lower energy, goes to infrared, and going outside of that lower than 400 nanometers is going into ultraviolet or higher energy. But what we see is 4 distinct lines. And you're going to see this every time you do this to hydrogen, right? Those are specific to transitions, right? So in fact, it turns out that they all come down to the second quantum level, right? So the one that's highest in energy is from from 6 to 2, and this is from 5 to 2, this is from 4 to 2, and this is from 3 to 2. Okay, so that's the one that's lowest in energy, and this is the one that's highest in energy, and so you can actually, and so this is really unique for hydrogen, and so we can distinguish all of the elements by doing this. And there's an instrument called atomic absorption that takes advantage of that, and you can analyze a sample and tell its chemical composition by it, right? At least qualitatively. You see all these different here, like lithium and sodium and calcium. If you burn these and then send the light that's given off through a prism, you can split that into a line spectrum. All right, so focus on the hydrogen here, right? So once again, what we see is we see the energy transitions only back to the second one. So once again, this is the 6 to 2, and then this is the 3 to 2, the one that's closest to the infrared here in the red. So red light's going to be lower in energy than purple and blue light. This is a summary of this, is again for hydrogen only. And here are the 4, and we call them the bomber series here. Those are the ones that I was referring to: red, green, greenish, and blue, violet. Well, blue and violet is what they call it, right? So those are the ones that are in the visible range, right? We can see them. Okay, but there are others going on. There are those that are really large in energy, high in energy. Those are that are coming back down to the first quantum level. And so they're in the ultraviolet range because they're higher in energy, so. And we cannot see them. And then there are those that are too low in energy. They are in the infrared, region, right? So those are the ones that are coming down from the 5th to the 3rd, or the 6th to the 3rd, and so on and so forth. And those are the Paschen series. All right. This is just another view, just a different picture, essentially showing the same thing. I think that's enough. I think you understand that. Okay, let me take a break and come back and talk about this in more detail. There will be more calculations.